Okay, good day. This is AP Calculus. I am Mr. McColley. This is section 6.3. Let's jump right into it and keep this thing moving. Okay, learning goals. Today we're going to talk about solving differential equations that can be solved by separation of variables, which we've talked about, and I've used that terminology over and over trying to get us up to speed so that we understand what we're talking about when we get to here. We're going to recognize and solve homogeneous differential equations, and then we're going to use different equations to model and solve applied problems, and we're also going to talk about solving and analyzing logistic differential equations. I'm probably going to have to talk about this in class a little bit also. I think I'm just going to try and get the equations here in this presentation, and then we'll talk about specifics later. All right, so separable functions. A separable function has this form where you have a function that is in terms of only x, a function that is in terms of only y times the derivative of y with respect to x. Remembering that, and again, we usually use f of x when we're talking about a function. I'm just trying to use the definition that was from the book. So m is just some function that is continuous, n is some function that is continuous, and they are in terms of x and y respectively. And this process is called separation of variables, and we're going to solve this using integration. So this is just a real formal definition for some of the stuff that we've already done. Okay, so I thought I'd start with an easy problem right off the bat. And here we've got expressions in x and the derivative of y, and another natural logarithm of x squared. So separation of variables is we're going to try and get all of our one variables on the left on the right and all the others on the right. So I'm going to try to move my x's to the right, leave my y's to the left. So my first step here, I'm just going to leave it 2x. Y prime is equal to let's see here, let's add positive ln x squared, and I just add ln x squared to both sides. And then let's divide both sides by 2x, and we'll have change this y prime to dy over dx. And then let's see here, so let's bring this 2 down, use the property of exponents, or property of logarithms that lets us take this exponent down and make it 2 ln x over 2x. And then we will cancel out the 2's, and we'll have dy is equal to the ln of x all over x dx. We'll multiply both sides by dx. All right, so as in previous problems, we're going to go take the integral of both sides, and the left-hand side is very, very simple. The integral of 1 dy is just y. This one, on the other hand, is a little bit more complex. So let's see, what am I going to do here? It looks like I'm going to need some sort of substitution because there is no quotient rule for integrals. So I'm going to look for probably the most complex part. And I know a lot of times the most complex part is on the denominator. This time it's on the numerator. So I'm going to let u equal ln x, and then du is going to equal 1 over x. So hey, check it out. I've got 1 over x here. So let's say that this is going to be the integral of, well, it's going to be just u du. So I can say y equals, let's see, u squared all over 2 plus some constant c. And then plug back in, we'll say y equals the quantity ln of x squared all over 2 plus some constant c. Now, this is the general solution. And they tell us here that when I plug in 1 for x, I get 2 out. Well, okay. Well, I need to figure out what c is to get my specific solution. So if I plug in 2 here, and I go the ln of 1, that quantity squared all over 2 plus some constant c. Well, the ln of 1, we all know the ln of 1 is 0. So I get 2 equals 0 over 2 plus c. That means c also equals 2. So my particular solution is y equals the I don't like that. Y equals the quantity ln of x squared all over 2 plus 2, and this is my particular solution. Okay, there's my first one right there. Let's look at one that's a skosh more complex, and I'm looking at number 22 there. I don't have it written down, but it gives us dr over ds is equal to, let's see here, e to the r minus 2, and they use s. I don't like using s, so let's leave that x in there and make it minus 2x. And then they say that r of 0 is equal to 0. R of 0 is equal to 0. So we're essentially trying to find r of x. When we're done, our function is going to be r in terms of x only. Well, let's see here. If I want to do this, I got to separate these variables somehow. That's not going to be too difficult. And when we remember that property of exponents, if you have a to the x plus y, you can separate that into a to the x times a to the y. That's pretty simple. So what I could do is I could take this dr over dx and say that that is equal to e to the r times e to the negative 2x. And now I've kind of already separated them, which is kind of groovy. So I want to get my x's on one side and my r's on the other side. So I'm going to multiply both sides by dx, and I got dr equals e to the r times, let's see here, e to the negative 2x dx. And then I'm going to divide both sides by e to the r. So I'll have 1 over e to the r dr equals e to the negative 2x dx. All right, looking good so far. Now, I could take the integral of both sides at this point, and then I'd have the ln of, and I'd have a substitution here. But let's remember that if you have 1 over e to the r, we can rewrite that as 1 over e, excuse me, screwed that up. I knew what I was thinking about, but I didn't get it done. Okay, we can rewrite this as e to the negative r as a positive, or make it in the numerator. Remember these two, that's the definition of a negative exponent. So I'm going to rewrite this as e to the negative r dr equals e to the negative 2x dx. Now the good thing about this particular thing is now I can integrate. I've got all my r's on the left hand side. I can take the integral of that. All my x's on the right hand side, and I'll take the integral of that. That's awesome. We can do that. And remember, the integral of e to the u is just the integral of e to the u is du is just e to the u. And so I do have a u here. I have that negative. So I need to put a negative outside, put that negative with the dr. And this one, I've got e to the negative 2x. And so for me to, so the derivative of e to the 2x is just 2. And when it's just start over, let e to the negative 2x, let negative 2x be my u. For me to do that substitution, the derivative of negative 2x is just negative 2. So I need a negative 1/2 out front, and I need my negative 2 inside there. And I'm just going to rewrite it so it looks a little bit neater. I need my negative 1/2 integral e to the negative 2x times negative 2 dx, and now I can integrate both of these, and I have negative e to the negative r equals negative 1/2 e to the negative 2x plus some constant c. The reason I put the constant on this hand side is, again, we're trying to solve for r, try to get r by itself. So what can I do about this? Well, there's actually quite a bit I can do, and I think that my best bet here is to, well, first I'm going to cancel my negatives. I got 2 negatives, that's going to make it easier. And then I'm going to go, let's take the ln of both sides. So I've got the ln of e to the negative r equals the ln of, let's see here, 1/2 e to the 2x plus some constant c. And then I'm going to bring down my negative r, and I got negative r equals Remember, ln e cancels. And so I have the ln of 1/2 e to the 2x plus some constant c, whatever that is, and then we'll change that to a positive, that to a negative, and there's my function. Now, they want me to calculate a specific function, so when x equals 0, r equals 0, right here we're talking about a particular solution. So if I let if I let x equal 0, negative ln of 1/2 e to the 0 plus c. Well, what does that c have to equal? Well, for me to get 0 here, I have to have 1, and e to the 0 is 1. So 0 equals ln, and then I have a half plus c. And we just saw that to get ln of something to equal to 0, what's inside has to equal 1. So c, why did I close that? I don't know. Going crazy in my old age, I suppose. I need to have 1 here, so my c is going to equal 1/2, and my particular solution is going to be y. R equals negative ln of 1/2 e to the 2x plus 1/2. And I'm sure there's some simplification that we could do here, but I think I want to leave it like that for right now. All right, let's go. Moving on. We're going to talk about homogeneous differential equations. Some differential equations have variables that cannot be separated. So you can't do what we just did. And some of these functions are homogeneous functions that have the form, if you have some f of x times tx comma ty, so it's a function in x and y, then you can separate out those t's from both of them and get that original function without the t's. Now, if you can do that, we have a homogeneous differential equation where n is the degree of that homogeneous function. And then what we're going to do to solve it is we're going to use these following substitutions. What we're going to say is we're going to say y is equal to vx and dy is equal to v dx plus x dv. Now, this should look familiar because it is a form of the product rule. They took the derivative of this with respect to x, and remember, the first times the derivative of the second plus the second times the derivative of the first, and they got that. So the first thing we want to do is, I'm looking at example number 34, where they say f of x comma y is equal to x, let's see here, xy over the square root of x squared plus y squared. Now, the question asks us to determine, is this homogeneous? All right, is it homogeneous? So what we're going to do is we're going to plug in tx and ty. And then if we can separate out those t's and get them out in front and get this all by itself times some power of t, then it is homogeneous. So if I plug in tx and ty, I'll have tx on top times ty there, so I plugged in tx and ty, all over the square root of tx, and then I have to square that, plus ty, got ahead of myself. Fingers move faster than my brain. Ty squared. And so here's what I want to do. I want to try and factor out all of these t's if I can. So when I look at this thing, I've got t squared and then xy. And that's good because now I have xy times some power of t. And then if I do this, I've got t squared x squared plus t squared y squared. When I square both of those, that's good. And I can factor out from both of these two terms t squared. So I have on my top doesn't change yet, so t squared xy, and then I'm going to have the square root of t squared times x squared plus y squared. And again, the goal, trying to factor out all my t's so that I can say this thing times some power of t. Well, this is a multiplication, so I can separate it. And I've got t squared xy all over the square root of t squared times the square root of, I hate it when it does that, the square root of t squared times x squared plus y squared, and t squared, the square root of t squared is just t, so I'm left with, and then just to skip a step to keep moving here, I've got my t squared divided by t is just t to the first times xy over the square root of x squared plus y squared. So I have my original equation out. So this is homogeneous. This is a first degree homogeneous equation. And it's first degree because it's t to the first. When we would have done all of our factoring, we had a t to the second, it would be a second degree, or a 3, it's a third degree. All right, moving on. So how do we solve a homogeneous differential equation? Well, again, we need to remember that we're going to substitute y with vy. And I'm telling you, and without going through this whole process, again, I'm telling you this is a homogeneous differential equation. So we'll just move on. And then dy is going to equal x dv plus v dx. All right, we're going to use these two substitutions. But before I get that far, I'm going to move this over to the other side. So I have xy squared, and remember, we can't separate the variables here, so we're not even going to try, at least at this point. We're going to use this to try and these substitutions to do our dirty work. Anyway, so this is going to be times dy over dx. I'm just changing the y prime notation to another form of the differential notation, and I got x to the third plus y to the third. All right, let's do one more step. Let's bring this x over and let's go x y squared dy is equal to x to the third plus y to the third dx. Now I'm going to go through, I'm going to do my I'm going to substitute all this stuff. So wherever I see a y, I'm going to change it to v, and I already screwed up from the other page. Remember, where did that go? I should have said y equals vx. I don't know why I said it. Y equals vy. So vx. There we go. And so I've got x, and then I've got vx squared, and then dy is going to be replaced with this thing, x dv plus v dx. And so I've substituted in for y here, and I've substituted in for dy here. Just use these values. Equals, and then it's going to x to the third plus vx to the third, switching out our y with vx dx. Now, why did I do that? Well, this is going to allow me to separate these variables. So doing a little simplification here, I've got v squared x squared times x is going to give me x to the third v squared. And then when I distribute it to this thing, I'm going to have x to the fourth v squared dv. And then I'm going to have x squared times x is x to the third, v squared times v is v to the third. So I'm going to have, let's see here, what was it? It's plus x to the third, v to the third dx. So I just simplified this. I squared that, multiplied by x, and then distributed the two terms. And then on this side, I'm going to distribute the dx just for a step. So I've got x to the third dx plus v to the third, and let's do it in the same order that we did on the other side, Let's call it x to the third v to the third dx. And what's good about this is, notice I've got a positive x to the third v to the third dx on this side, and a positive x to the third v to the third dx on this side. Those two cancel. And then I can divide both sides by x to the fourth, and I get v squared dv equals basically 1 over x dx. And so a bunch of these things have now canceled out. I've got all my dv's on the v's and dv's on the one side, and all the x's and dx's on the right hand side. So now we've separated the variables. We can integrate, and we'd have v to the third over 3 is equal to the ln of x plus some constant c. We wanted to, we'll multiply by 3, get v to the third equals 3 ln x plus some constant c. We're almost done here. All we got to do is remember that y equals vx, so v equals y over x. Come back down, because we can't leave it. We can't leave a variable that we're just putting in the end. So we're going to make this y over x to the third equals 3 ln x plus c, and then we'll take y to the third and x to the third, and we'll have y to the third equals 3x to the third ln x plus c x to the third, because I'll have to distribute. Now, normally in the past, we just said we're combining a variable. I can't really do that here because x is a variable, so I can't make a new variable out of it. I have to have some constant c times x to the third. And for this, we will leave it just like that. It's our final answer. All right, our last one. And I'm already at 22 minutes. Okay. Let's see if we can't do this. You know what? At 22 minutes, I am going to call this the end. And we will stop there. And I will either do that one in class, or I will make a second video to do that one. And you can break it up into 2 parts, but 22 minutes is good enough. So have a good one. Goodbye.